just under. What is it?
Alright, I'll give it a try.
No. Try not. Do. Or do not. There is no try.
Wise words of wisdom from Yuga. Let's take a look at what we have today. We want to evaluate functions at a given value, here x at -2. To do that, I'm going to replace the value of x with -2 everywhere I see it throughout this function. So I have the square root of my value x plus 3 plus my value x squared minus my value of x cubed. And in this case, my value of x is -2. So I will insert -2 for all those values for x. When I do this out, I end up with f of -2 is equal to the square root of 1 plus -2 squared minus -2 cubed. Well, the square root of 1 is 1. -2 squared is 4. And -2 cubed is -8 times -1 is plus 8. Altogether, this gives me 1 plus 4 is 5, plus 8 is 13. So f of -2, value it's to be 13. On to the second one. I again am going to replace every value of x with -2. Throughout my entire expression. Once I do that, I can simplify things pretty easily. -2 plus 2, 0, plus, and then the absolute value of -2 is just 2. So I end up with 0 plus 2 over 2, which is just 1. So f of -2 is equal to 1. Moving on. Find the domain of each function. Whenever we're finding the domain, we're going to assume that it's all real numbers and then look for specific restrictions. In this case, since I have a real valued function, I cannot take a square root of a negative number and get a real numbered answer. So my restriction will be that what I'm taking the square root of, which in this case is x plus 6, has to be greater than or equal to 0. When I solve this out, I get x is greater than or equal to -6. This would be my domain, my values of x which are possible in this expression. You could also write this in interval notation, which would be from -6 to infinity. On to the next one. Here, again, I'm going to assume that all real numbers would work and then look for restrictions. In this case, I have a fraction, so I cannot divide a fraction by 0. This would give me an undefined answer. So instead of assuming it's all real numbers, I'm going to look to see if there's any place this fraction is undefined. Well, that would happen when x squared minus 9 is equal to 0, or when x squared equals 9, or when x is either positive or -3. So my domain would be all real numbers with the exception of x being positive or -3, so x not equal to plus or minus 3. Next. Even and odd functions. Well, odd functions are symmetric through the origin. Even functions are symmetric through the y-axis. There are tests for even and odd functions, which are if f of -x equals f of x. This is an even function. And if f of -x equals -f of x, this is a odd function. Remember that these even and odd functions get their name from the powers of the functions we're talking about. So my expectation is that this function will be odd and this one will be even. However, my expectations might not always be true, so I should check it using this test regardless. So let's take a look at each of these. For the first one, if I plug in h of -x, I end up with -x to the 5th minus 3 times -x. This turns out to be -x to the 5th, when I evaluate -x to the 5th, plus 3x. Well, this is just equal to -x to the 5th minus 3x, which is itself h of x. So here I have an expression, h of -x equals -h of x, which makes this a odd function. For the second one, I'm going to do the same test. plug in g of negative t, and I end up with 2 times negative t to the 4th minus 5 negative t squared, which is equal to 2 times t to the 4th minus 5 times t squared. When I raise a negative to a 4th power, it's an even number. I'll have an even number of negatives, which will make a positive. Same for the square. When I square the negative, I have an even number of them, which make a positive number. What I end up with is g of negative t is equal to 2t to the 4th minus 5t squared, which is in fact g of t. So g of negative t is equal to g of t, which makes this a even function. This test also works for trig functions and any other type of function that you might look for. So just not just for exponents, but any other function type as well. Okay. Sketch each function and its transformations on a set of axes and label its graph. Here, f of x equals x squared. Well, that's my base quadratic function, so I should know offhand that this looks roughly like a parabola centered at the origin. Not centered, but its vertex is at the origin. Looking at g of x, I am subtracting 3 from x. This is equivalent to a shift 3 units right. So I'm going to go 1, 2, 3. This is where my vertex will end up, and I will have roughly the same parabola, just shifted over. And h of x equals negative x squared plus 1. Well, negative x squared is going to reflect my original parent graph, and then I'm increasing its vertex by 1 unit. So its vertex will move up 1, and it will be flipped across the y-axis. Those are my 3 sketches for each of those graphs. Moving on to the second set. Again, my first graph is the square root of x. If you recall, the square root of x is a domain of values of x greater than or equal to 0, and a range of values of y greater than or equal to 0. And it sort of looks like half of a sideways parabola. This is my square root of x function. For my second one, g of x, which I'll do in green, I'm taking that function and shifting it left 5 units. So I'm going to go 1 over 1, 2, 3, 4, 5. Same function. This is the square root of x plus 5. And for my last one, what I do to my parent function has the exact same value, all subtracted by 3. So I'm moving it down 3 units in the y direction. 1, 2, 3. It's the square root of x minus 3.